The first problem on the homework, I got a different answer. I thought it should be 248 over 249 because so it's like you had 1,000 memory accesses.
Okay.
And it seemed to me that the prefetches would be to 8, 12, 996 up to 1,000, and like it seems like.
Do you? I need the question first.
So I haven't looked at the question in a while. Do you want to take that, Loanya?
I can. I need the question though. I need the question though. I don't remember it off the top.
Yeah. Is there a mistake in the answer, or?
I don't know. I check.
Okay. I mean, if it's just a simple mistake, I'm not sure if you want to go through the homework on that question, unless you guys want to.
I don't think it's a mistake.
Oh, you don't think it's a mistake? You don't think there's a mistake? Yeah. Okay. So let's take a look. I guess let me project it. So you found 248.
248 over 249.
Okay. Oh, we need to do that. What happened? Yeah, it's a laptop, which is what we want. Oh, it's not on? Okay. Okay, I think it's fine. We can keep only one of them. So, we don't know if this is there yet.
Do you have a hard copy?
No, I don't here.
Okay, sure.
Okay, so does everybody have homework 7 in their hands? I don't think pizza will help you in this case. Well, that's supposed to be warming up. Otherwise, to display. Okay, there it is. Good. So, what does this say? It says an architect has designed a prefetch engine for his machine. He first runs 2 applications A and B on the machine with a stride prefetcher. Application A, so you can see that striding through this array, right? And summing up all of the array elements. Application B, this is doing the same thing except it's starting from I equals 1.
And it's multiplying the iterator by 4.
Oh, wait, it's multiplying. That's right, yeah. It's multiplying. Okay. So that means the first one has a stride, but the second one doesn't, right? Because you'll start with 1, and then address 4, and then address 16, and then address... I guess you could detect that pattern too, potentially, right? You could potentially design a prefetcher that detects that, but that'll be more complicated than a simple stride prefetcher that looks at the last 2 accesses and subtracts one from the other, right? Okay, so the question is, I and sum are in registers while the array A is in memory. The cache block is 4 bytes in size. And if you look at this, each element is 8 bytes, right?
Mm-hmm. No, 8 bytes, yeah.
Oh, 8 bits.
8 bits.
Okay, so each element is a byte. Okay. Okay, so let's see. Well, here's the solution. Looks like this is the solution. So the question is, what is the prefetch accuracy for applications A and B using a stride prefetcher? So we'll look at A because that's the one you think should be 249. Right? The stride prefetcher takes a stride between 2 consecutive memory accesses and prefetches the cache block at this stride distance from the currently accessed block.
What does that mean? Like,
so
how can it be the distance between 2 addresses, but be in terms of block? I mean, like,
so basically, stride prefetcher works on the cache blocks, right? There's no point in working on the individual cache accesses. Where's the? Okay. Let me find the. You guys see it somewhere over there, or do I dig through this? There's supposed to be a big one that writes better, and it's more easily visible. I guess I'll make do with this for now. People in the back may not be able to see it. But so let's say your array is like this, right? What you're doing is accessing A0, A1. Is that true? No.
A0,
A4. Yes. A0, A4, a 8, let's say 12, right? And it turns out these are two different blocks, right, in this case, because your cache block size is 4 bytes, and each element is 1 byte, which means when you access A0, you bring in A0, 1, 2, 3. So this is a cache miss. The next address you access is A4, and that's a cache miss, right, with that instruction. And the distance between them is, if you think of, in terms of cache blocks, it's one cache block, right? That's your stride. Okay. So initially, the stride prefetcher, what happened there? Okay.
Yeah, it's coming up. It's come back up.
Say it again?
It's come back.
Yeah, maybe because it's going to sleep. Let's prevent that. So initially, the stride prefetcher, and this is, it detects that initially the stride prefetcher has no information, right, about these accesses. And let's assume there's a one entry stride prefetcher. So it sees address A0 and records it, which means that you cannot prefetch this. Okay. So you was it prefetched, if you will? And the answer here is no, it wasn't prefetched. And then the next access. But now it doesn't have the stride, right? This is the previous access, previous address, if you will. And then this is the stride, your stride prefetcher entry. Stride is squiggly, if you will. You have no idea what it is, because you didn't have anything to begin with. The next access, the stride prefetcher sees A4 and computes a stride. Remember, let me write this in terms of cache blocks. If you write it in terms of cache blocks, let's say this is cache block 0, this is cache block 1, right? So what you do is subtract the previous address from the current address that the processor is accessing, 1 minus 0, and set your stride that way. Right? And previous address is now 1, so move to the cache block addresses. Is this clear to everyone? Now you set your stride, but you couldn't prefetch this because you didn't have your stride. But now you can prefetch. Now you know that your previous access was A4, and you have a stride, not your previous cache block address. Was 1, and you have a stride of 1. So you could actually prefetch 2. Right? You send out a prefetch for 2, and the processor accesses 2. Right? So you could prefetch this. And when the processor actually accesses this, the previous address is now 2, and stride is still 1 because 2 minus 1 is 1. So on. You will prefetch this. You'll prefetch all of them because now your stride is the same as the stride of the access path. Yes?
So the stride doesn't have to do with the addresses, it's like the cache.
So you could do it the other way around. You could just look at the addresses also, right? If you did, then what would happen is, so this is in class we discussed a prefetcher that works on cache block addresses. You could design a prefetcher that doesn't work on cache block addresses, but just looks at the absolute addresses. Then what this would look like is this. Previous address, stride. Then your stride is really 4, right? And your previous address will be 0, 4, 8, 12, 16. And your stride will still be 4. But I like thinking of it from the cache block point of view, but there's no real difference.
Well, isn't there? I mean, because this just works nicely because your stride happens to be a multiple of the cache block size.
Mm-hmm.
Like, if say it were 1, right, then instead, if we first fetch 3, then that should be fetch 4. If we're doing it by PC,
Wait, let's finish the question, right? The question, so your question is answered?
Well, I mean, no.
All right. Okay. So the question says, let's go through this. The question says, what is the accuracy of the prefetcher, right?
Yeah, but that's not.
Which means you will miss. What is the accuracy? What is prefetcher accuracy? This is number of accesses prefetched
Okay.
divided by
I see.
Yeah,
It's
I don't
coverage,
think
right? Yeah,
that's
I see
right.
his problem.
Okay. Well, I haven't looked at the solution yet. I'm just answering the question. This is the number of accesses prefetched divided by total number of prefetches sent, right?
But in lecture,
So how many prefetches did you send? 248. Why 248? Because you have 1,000 things, and divided by 4, you have 250 accesses here. So this is 248. You have 250, but you didn't send prefetches for 2. How many accesses actually you prefetched accurately for? Well, that's again 248, right? Every prefetch you sent was accurate. So that the answer is wrong. You're right.
but that's not the formula you gave in lecture. The formula you gave in lecture was the number of prefetch used over the total
Yes.
number of prefetches.
That's right. Yeah, the first one is the number of prefetches used, if you will, right?
No, that's the total number of prefetches.
So this is the total number of prefetches, bottom part, right? And how many of the accesses were actually how many prefetches were used basically? You could think of it that way too. Sure.
Okay, yeah, because
Let me clarify it. Even if we want to be consistent with the lecture, number of prefetches used by demand accesses.
Isn't the actual number of prefetches 249? Because when you do the last one, 996.
Okay, that's a good
you'll
question
also
also.
fetch 1,000.
I guess the boundary condition is not covered. You're right. If you're, I guess at the very end, you're right. So if you go to, what is that? Is that 240?
Well,
996.
996 and you're fetching 1,000.
Yeah, A996, right?
Yeah.
That gives you 250? Okay. So when you actually access A996, you're going to generate a prefetch for A1000. Which means that you will send one more prefetch, which is true. So this will make it 249.
But it's undefined if you use it or not. It depends what comes afterwards.
Well, the assumption is that program ends there, yeah. There are a lot of assumptions. But you're right. I mean, you found the bug in the non-linear solution, I guess. So this is wrong, right? This is really coverage. Is that coverage? What do you think?
Yeah.
So if you look at, I assume you asked the coverage on the next question.
No, there isn't.
Okay.
There isn't coverage.
So let's do the coverage then. What is coverage of this prefetcher? So did everybody get the accuracy? What is coverage? Coverage is total number of accesses made by the program. Made by the program. This is the denominator. And number of accesses that were actually prefetched by the prefetcher. So how many accesses does the program make? 250. We've already figured that out, right? And how many accesses were actually prefetched? 248 of them were prefetched. Okay?
Are
Yes?
those just accesses that were prefetched correctly, or accesses in general?
Yes, access is prefetched correctly, yes. Because an access that was not prefetched is not... A prefetch that was not correct cannot have been an access that was prefetched, right? Because it's never used. Okay? Yes, you have other questions? So that answers your question, right? Okay.
In this same exam question, I have a question for part B1.
Part B1, okay.
So, like, how can you improve this?
This one, this part?
Yeah, basically suggest a prefetcher that would provide better accuracy. Like, why couldn't you use software prefetching for that? Because then you could get 250 over 250 since it's
Yes.
not dependent on your...
So that could be an answer, right? That could be another answer. You could. There are many answers here, right?
I mean, you want to improve it on 248 over 249.
That's right. Yeah, that's the goal. So if you do software prefetching in this case, that's a valid answer.
Because it's not dependent on input set.
Yes, you could start prefetching earlier, right? You could have a loop that starts prefetching before the iteration, or you could start perhaps even earlier. Maybe there's a previous loop. So you could get perfect accuracy if you time your prefetches right.
So that could be something that's valid then.
Yes, that would be a valid answer for this. I guess your answer was having a higher prefetch degree. Is that true?
Yeah.
Okay. But that will not necessarily improve accuracy, right? That would, again, this is coverage, I think. So this is, the question is asking accuracy, but the answer is answering coverage. Don't do that on the exam. So the answers would be perfectly valid if the question was asking coverage. Does that make sense? These are different things. So if you want to improve coverage, you would like to have a larger prefetch degree. If you want to improve accuracy, I'm not sure, you need to design a different prefetcher, like software-based prefetcher.
Can you improve coverage using the software as well?
I mean, accuracy can also be improved with the next line, right? Because you'll prefetch. Well, no, not really.
Yeah.
Sorry.
I mean, you could improve accuracy. Instead of using a scribe prefetcher, you could do a next line prefetcher that always prefetches next line, right? That way, you would prefetch this block. So you would actually do 249. Oh, that's right. That's the next line prefetcher. So I guess your answer works.
But a prefetch degree of 1 would do.
That's right. Yes. It should be a prefetch degree of 1. Okay, you should correct
Yes,
this answer.
I'll do that.
Does it make sense? Okay, let's go back. So we want to improve the accuracy of this prefetcher, scribe prefetcher. How do we improve accuracy? Accuracy is 248 over 249. And we did not prefetch two things. So we have only one thing that's incorrect. That's at the end. And we have a total of 250 things that we can get correct. So with using a scribe prefetcher, I don't think you can improve the accuracy. You need to do something else. You need to somehow prefetch these blocks. How can you prefetch these blocks? If you use a next line prefetcher that actually prefetches the next block after it sees the current block, then the next line prefetcher cannot prefetch this one because it didn't see the previous line. But once it sees this block, this line, it would prefetch this one, and it would be correct. This is the next line. And once it sees this one, it would prefetch the next block, so on. So the accuracy of that next line prefetcher would be, I guess, next line. Again, number of prefetches sent. How many prefetches would it send? 249. And at the very end, one more incorrect prefetch. 250. How many prefetches were used? Well, 249, right? So this improves the accuracy just a little bit. Instead of 248 over 249, you get 249 over 250. Make sense? Now, if you do software prefetching, you can potentially do 250 over 250. I'm not sure if you can do, without making other assumptions, I'm not sure if you can get 250 over 250 with just hardware prefetching. Okay?
So, in general, does software prefetching improve accuracy or coverage or both?
No, it really depends, right? It could degrade accuracy or coverage also, right? If it's a pattern that doesn't look like this, that's not easily prefetchable like this, it could degrade your accuracy. So there's no way you can make a general statement.
Right. But like for an access pattern that's similar to this one.
Again, it depends on where you place your software prefetches. Right? If you, for example, don't do the right thing and start prefetching here, I don't think you can prefetch the first thing, right? You might be able to, but you're going to use it right away anyway. Right? Okay. Okay. Any other questions on this? We want to do the coverage of the next line prefetcher also. That's easy, right? Okay.
Also, I mean, it seemed like going by hash block and going by addresses isn't equivalent though, because isn't it only equivalent when when the scribe is a multiple of the hash block size?
So that's why a lot of the prefetchers work on cache blocks, because it really doesn't matter if you look at the address itself, right?
I mean, they're different. Like, if you fetch 3 and then you have stride of 1, then you prefetch 4, so that time it would be the same. But then when you have 4, it would not yet prefetch the next block, right? Because it would be thinking about 5, whereas the stride prefetcher with the cache blocks would instead go ahead and fetch the block after that.
So you're saying you could have a stride that will not lead to a stride in the cache blocks. Is that correct?
Well, just the blocks that are fetched could be different or at slightly different times.
That's right, yeah. It could be slightly different. That's right. It's not exactly the same, you're right. But for the class, we will remember in one slide I said, assume that we're going to do a cache block-based prefetching, right? And all processors today do a cache block-based prefetching. So assume that for the exam. That's what I... Don't think about the actual address, because in the end you have the address, and what the processor brings, it chops off the block object, right? You bring a cache block that contains the address. Okay? Okay.
So, if there's a question for whatever reason asked, like what the stride is, we want to answer one. Or would it be?
We'll specify whether we want the stride based on cache block or based on the actual address itself. Okay. Okay. Anything else? Yes.
So in lecture we said that for like one of the reasons for doing multi-threading is that like it's more power efficient to have 4 units running at a frequency of f over 4 than it is to have 1 running at f.
Okay. Yes.
I don't understand why.
So I guess let's go through that. This was motivation for multi-core, actually. Right?
Yeah.
So, and there were assumptions there. Assumption, you can parallelize your program perfectly, right? Let's write that assumption. I guess perfect parallelization, if you will. And assuming, again, another assumption is frequency is your only knob, if you will, right? So remember the power equation I wrote, right? Power equals activity factor times capacitance, overall capacitance that you could present a chip with, voltage squared times frequency. Now what you can do is you can either have 1 unit running at frequency f, and the other option is, I guess let's go with 4 units. Let's be concrete with a number. Running at frequency f divided by 4. Right. These are the 2 comparison points. And you have a program, and that program here finishes at time t. If you can perfectly divide your program, divide your work. Let's say your work is W. If you can perfectly divide your work, W over 4, and these are perfectly parallel, this will finish at time t also, right? This will take same amount of time as this. Is that correct? Okay. Assuming perfect parallelization again. So what will happen is, well, what you've done essentially is, without changing the execution time, change the power. And this is, let me clarify this a little bit, this is dynamic power. So, dynamic power of this is alpha C V square F. And assume that the capacitance and alpha remains the same. That may change also. And here, alpha C V square F over 4. Right? So we reduce power, for sure. So one other thing, here the power is F over 4, right? One other thing you could do is, once you scale your frequency, you could scale the voltage because you don't need to support as high of a frequency. And assuming you can do linear scaling, linearly scale your voltage, you can divide your voltage by 4 and you get, I guess, 64 times reduction in power. Is that correct? Yes. So there are a lot of assumptions that I made. I walked you through all of those assumptions. But even if you do not do this, you're more power efficient.
Isn't that per core though?
This is per core. That's right. Yes.
So if you want to consider...
So if you multiply, so I guess again it depends on how big of a core. That's why I draw the big core here. Right? This is 4 times the area. This is another assumption. Implicit assumption I made is this is 4x the area, and these are x the area.
So aren't we comparing like one processor versus the total of 4 processors, or are we comparing one versus one small?
What do you mean? So here we're comparing, assuming you did this, we're comparing the total of 4 processors, right? This is 4 times less the area. That's it. So when I gave this example in the lecture, I gave the example of multi-core. Your one option is build a huge core that runs at high frequency and that does other things, occupies a big area. Your other option is divide that core into smaller cores that occupy smaller area and that runs at lower frequency. That way you can reduce the power consumption, assuming you can parallelize it perfectly. Okay? And you could do the comparison many different ways, but this was just one way I did the comparison. You could now compare this with this, right? You could have actually X only. But that's not really motivation for multi-core. Because if you can do this, you're really increasing the area. Yes?
So you reduce the power per core moving from the left example to the right, but the total power is the same. Is that true?
You reduce the... No, the total power reduces also, right? Power per core reduces and total power also reduces.
Oh,
So-
because of the voltage. Okay.
Yeah, because of the voltage and frequency. Yes. Yeah.
But if,
I mean, yes, you can. There are a lot of what ifs you can come up with here, because lots of assumptions, right?
if you
Go
couldn't
ahead.
scale the voltage, in that case would your total power still reduce only because of frequency?
Okay, let's think. You mean if you couldn't scale the
Yeah,
voltage,
yeah.
you're saying? So let's not scale the voltage.
The- Then it
Did it reduce?
No.
In this case, it didn't.
Still have to multiply this by 4.
Yeah, I guess it really depends on the other assumptions that you're making, right? I made the safe bet by making this 4x.
No,
So again-
given all that, given every assumption that we've made so far,
Okay. Yeah, then it won't reduce. You're right,
it won't. Right?
because assuming we follow all of this, you'll have 4 of these, right? Okay. Yes.
Under what conditions can you scale voltage?
Okay.
Is that like a black box?
So that's not if your voltage is high enough, you could usually scale it. But if your voltage is very low, which is the regime we have today, actually, then you cannot scale the voltage and frequency don't have a linear relationship. So today, this doesn't hold very well. 20 years from today, well, before today, 20 years ago, it held much better. Yes.
So when you write all the x's there in the 4x, are you saying that power scales with area? Or because the question is, so first of all, does that quantity you wrote there, is that the power per core there, or is that the total power?
So let's assume that this is power per core. Then you need to multiply this by 4, right? Because that's the assumption.
Okay, so
Okay.
it doesn't. So it's just a coincidence that it also is 4 times the area.
That's right. Yes, that's right. It happened to be a coincidence in this case. Yes.
Will the capacitance be affected by the area?
Yes. So there are a lot of assumptions, right? That's an implicit assumption that I didn't make. So if you had this 4x, maybe your capacitance is high also, right? So it's hard to keep everything constant. I just want to give you the basic idea at that point. So don't take this too literally. This was the motivation for multi-core, right? I'm not going to ask you a question in the exam. Calculate the power for this.
I was just wondering.
That would be an unfair question, right? Because that's something we did not really cover in class. So, or voltage frequency. I know you guys are curious. That's why you ask. But I wouldn't ask you a question. Tell me the relationship between voltage and frequency. That's not the topic of this course. It's good for you to know, but it's not the topic of this course. Now, I might ask you this equation, right? You covered this, so you'd better know the terms of this equation. Okay. I don't know why this projector likes projecting that, but it's happened in our regular lecture room that you don't see this, right? Maybe there's a setting somewhere here. Okay. Is this clear? Okay, maybe we should do fairness in terms of questions. Nobody else has a question? I'm going to Eric again.
For question
Okay.
two,
Yes.
it said it's so one condition is where the program is running completely parallel. So
Question 2. This is Amdahl's law?
Yeah.
Okay.
So how can you have load imbalance if it's running completely parallel?
Amdahl's abstraction of a parallel program. You should ask Molly this question, probably. Represents a parallel program as two portions. One in which the program is completely serial, the serial portion, and the other in which the program is running completely in parallel, the parallel portion. In practice, the parallel portion doesn't achieve perfect speed up. Why is this so? So this is the Amdahl's abstraction, right? And we're saying, why is this not a good abstraction? So this is asking why is the parallel portion? Well, why is the parallel portion not perfectly parallel, basically? And there are three fundamental reasons that we discussed in class. Synchronization, so you got it, I understand. Synchronization, overhead, load imbalance, and shared resource contention. Right? Amdahl's law doesn't model these, because what it assumes is, remember Amdahl's law, speed up equals 1 divided by 1 minus parallelizable portion plus parallelizable portion divided by n. This holds only if this parallelizable portion is perfectly parallelizable, right? Perfectly divisible by n. And it's not perfectly divisible because of these things that we discussed in class. Okay. Looks like we have only 2 people asking questions. Come on. There are lots of questions to ask. Yes?
So, we spoke about the simple invalidation-based cache coherence cube. So, I don't understand the one of the arcs in the state transition diagram.
Okay, so let's figure out what those arcs are. Actually, let's go to the lecture site. That's probably... Oh, it's here. This is the mod synchronization coherence lecture. Let me recite this. Okay, that's better. It's been a while since spring break, huh? Okay, it should be in this lecture. Oh, that's the parking ticket I got. You don't want that to be on the exam, probably. So there was a race condition between the person who's giving me the ticket and me paying the ticket, so I'm going to dispute that. I guess race conditions happen a lot in the coherence protocols as well. So where is the simple coherence? Okay, just one?
Yeah.
By the way, how did people like the last lab? Is that a bad question to ask?
Yeah, it's a very bad question.
Okay. I know some people finished it. How many of you guys finished it?
Doesn't imply it's
Are you talking about getting it 100% working or just getting it working?
How many people got the cycle counts correct?
Almost.
Oh, there's 1, 2, 3, 4. They're shy. That's okay, you don't need to be shy. How about almost correct? That's good. That's good, that's quite a few.
I think the problem with lab is that it just tells you what to do without explaining the computer and its like background of it. So it's kind of bothers.
Without explaining why.
Yeah, without explaining exactly why you do it. So it's kind of like it just tells you the steps of coding.
Oh, why is in the lecture, right?
Well, yeah,
Is
we
that-
want to reinforce it through a lot, and like this lab, it was kind of just make sure you read it exactly how it was intended.
Yeah. Well, otherwise, if we just told you implement the state machine, what would happen is you would not get the cycle counts correct.
Yeah, so you can't rely on it at all.
Say it again?
Like it would have been better just not have a lab at all.
Well, I think you learned something, right, about from the lab.
Specifications can be ambiguous.
Yeah. Yeah, that happens sometimes also. Yes.
Going forward with it, I would say hand this lab out when you first give out the simulator.
Okay.
So that each lab builds on the previous ones, but if you don't know the architecture you're going towards, you may have to significantly restructure it every single lab, depending on how you do it. If you have some idea of what you're headed towards, you can set it up initially with that goal in mind.
Okay, but then you need to know, like what coherence is, if you will, right?
Well, you just could have said, like, lab session is going to be multi-core, so make sure that you code it so that it'll easily translate. That would be fine.
So like instead of
Yes,
using global state, you can
Yeah, I guess we could do it. Yeah, this is good feedback. So maybe going forward, we'll try to make it easier in the future. But this is, you implement a real coherence protocol, basically. This is what's implemented in Pentium Pro, as we discussed in class. So I think it's a very valuable experience. You may not have finished it. That's true, and I will take that into account in your grading. There is no question about that. I'm a fair grader. But for those of you who actually had time to finish it, you did something that is done in real systems. How many people couldn't finish it? Okay, that's quite a few. That's fine. I'll take that into account in the grading. So we'll do extra credits. I'm curving the course anyway, so you don't need to be worried too much if you didn't finish lab 7. Okay? But if you want to do it after the class, you're more than welcome to learn. Okay, so let's go back to this question. So this is simpler than the coherence protocol many of you implemented. And this is, in a sense, it's a dumb protocol, right? You have two states, valid, invalid. Okay, I don't want to go through the state diagram, so what do you have a problem with?
The processor write and invalid state.
Okay.
Why does it have? How can it
Okay. So here, let me see. Right through, right? That's why. So there are assumptions here again. So if this was a write back, then you would need to bring the block and make it valid. You're right. Write through, you don't need to bring the block. And no write allocate, actually. No write allocate. When you write, you're writing through, and you're not allocating the block, which means that block stays invalid.
You just write all the way down.
Exactly, write all the way down. That's fine. So if this was, actually that's a very good question, right? This could be a nice exam question, if you will. I'm not suggesting it will be on the exam. How would this diagram change if you had a write back and write allocate cache? Now what would happen is, when the processor write happens, you send a bus write signal, bring the cache block and make it valid. So that would take it to valid state. So these state diagrams clearly depend on what your cache is, right? What your other caching policies are. Okay. That's a good question, though. Good catch. I think I briefly mentioned it, but we went over this very fast. What else? I hope. Okay, there is one more person who's studying for the exam.
See lecture, we have gone over the sequential consistency part.
That's right.
But I got confused when I looked at some of the examples where you gave.
Okay. Where did you get confused? So sequential consistency.
This is fine.
Okay, you remember, right?
Yeah, over here.
Okay.
So, for for one processor, A has to come before B, right?
A has to come before B, that's right. And I hope it does.
But then what is this? Oh, this is...
There's all potentially incorrect global orders. Maybe I should have labeled order 1, order 2, order 3, order 4, order 5, order 6.
I'm sorry, I was reading...
Yeah, in class I showed you, but here I did not, right?
I was reading it.
Yeah. In class I showed you this way, right? A, B, X, Y. Yeah, it doesn't make sense if you read it wrong. You know the 3 A's and the 3 X's, right? Okay? So if you remember, this was the order. Yeah, it's always top down, right? So I'm consistent here. So processor A, it does ABX. Processor, this is, no. We better go back one more. Yeah, processor processor 1 reads A and B. Processor 2 reads X and Y. The question is, how does it appear to other processors? And as long as you have a single total order that's the same for each processor, you satisfy sequential consistency. That's the idea of sequential consistency. You have a single total order that's globally the same for every processor. And these are the potential single total orders. A, B, X, Y satisfy sequential consistency as long as all processors see it that way. AX, BY, AX, YB, XA, BY, so on. Okay? So that's clear now. What else? I hope you guys can read my writing. But this is in the Lamport paper also. Lamport talks about, I guess Lamport doesn't talk about debugging. Okay. Yes?
I'm wondering why we can't have one fixed global order for once we execute it.
Across different executions?
Exactly.
Okay, that's a good question. Why? Because the order in which you acquire locks, let's say threads synchronize. Right? And when you synchronize, one thread may reach the lock earlier than the other thread in one execution, whereas in another execution, the second thread can reach the lock earlier than the first thread. And this really depends on when the threads are scheduled onto the machine. So you have thread 0, thread 1. Let's say one execution 1. It does lock A, and thread 1 does lock A later on. That's the order. The next time you execute the same program, again thread 0, thread 1, even with the same input set, it could happen such that thread 1 reaches the lock A first, and thread 0 reaches lock A next. Why could it happen? Well, because in the execution 1, let's say you had some cache state. One example. There are many reasons, right? Thread 0 is running on this processor, thread 1 is running on this core. And this cache was initially empty, whereas this cache was warmed up. Well, let's do the other way around. This cache was warmed up, and this cache was empty for some reason, right? Because something else ran before. And it so happened that this thread executed faster and reached lock A first. In the second execution, the initial condition was when thread 0 started, its cache was empty, because something happened, or empty meaning some other thread from some other program executed, so it's useless for thread 0's purposes. And for thread 1, it was warmed up. It had all the locks and everything it needed in the cache. Now it executed faster in this execution, and it reached lock A. That's why different executions can lead to different orderings of the threads. And this makes parallel programs hard to debug. If you have a bug that happens only when you have this kind of order, it's very hard to catch by running the program again, because you get a different execution order. Okay? You guys have debugged multi-thread programs before? Yes, some of you have. If you've taken an operating systems course and dealt with threads, you would know this very well. Now, the good thing is actually we didn't make your simulators multi-threaded. Some commercial simulators, like the simulator that was used to develop Pentium 4, Intel Pentium 4, it was a heavily multi-threaded simulator because they wanted it to be fast. So events like when you're doing a load, that would generate a thread that executes and models the execution of the load. Yes.
How do they ensure they got every single one?
How do they what?
How do they like verify that they got every single one?
How did they verify the simulator, or how did they?
Well, how do they verify the processor? Because like the simulator does it in one of these execution orders, then it's not checking every possible order, so it's not verifying the processor.
No, this is different, right? You're simulating the processor with a multi-threaded program. So the processor you're modeling is separate from the simulator that models it. Does that make sense? Okay. I just want to give you an anecdote of a multi-threaded application. So debugging that simulator was hard, basically. That's the that's the final verdict, if you will. But it was a beautiful simulator. Okay, what else? Yes?
I have a question for in lecture 22, slide 31.
Okay. Let's go to lecture 22. I guess I'll close it because my PowerPoint. Okay. I guess that'll take a while. Lecture 22. Slide 31, I just said. Okay.
Yeah, so it asks, I think, which one is better at one point.
Say it again?
If you go further, a little further.
Okay.
Yeah, so it asks which one's better.
Yeah.
And I would say, like, the reason behind, like, which one is better depends on how early you want to prefetch, right?
Uh-huh.
Is that the answer?
So here, actually, if you remember that, if you go back to the lecture, this is not different from this, right? Because what you're doing is really traversing 3 iterations ahead.
Yeah.
So you cannot do this, if you will. Here, what you're doing is you're prefetching the next iteration's pointer. But here, if you try to do next, now you have dependency. You need to prefetch this first, and after you get that result, you need to prefetch that next. Then it says you cannot do this. Right? I mean, you can do it. You can have it in the code, but it won't help more than the previous one helped, because you would stall. Actually, it may be worse than this one. I don't know. I need to think about it a little bit. But what happens here is you send a prefetch, you continue with the work, and then after that pointer is set to pointer next, and then hopefully that pointer next is prefetched in the next iteration, you use it. So assuming that you have enough work to overlap with the prefetch of this next one, you're good. Whereas here, you send this prefetch, now you need to wait for it to get back to be able to send this next. And that'll take time. Which means that you cannot keep going on the work. Right? So this could be worse on an in-order processor. Make sense?
Makes sense.
So that's the difficulty of prefetching pointers. You cannot prefetch ahead, if you will, because you need to dereference next. And we talked about in class skip lists, right? You could potentially have pointers pointing to far away places in the code. Yes?
Potentially you could prefetch that. If you prefetch like P next already before, like if you're like working into the distance now.
Yeah, if you had done it, but this example didn't do it, right? If you actually Yeah, you need to do significant code engineering to actually do that. Okay. And yes, this example doesn't consider the null pointer case. That's another issue, right? You need to consider that. Well, you could have prefetch instructions. When a prefetch instruction references a null pointer, it basically doesn't generate an exception, right? Non-accepting prefetch instructions, if you will.
What is that first evaluate the pointers? Just install
This one?
The second one, like, you never they would evaluate the arrow next to
That's right, yes.
Before going to
That's right, yes. So it would stall the pipeline, right? Yeah, that's the problem with this.
That's fine.
What else? So now we have 3 people asking questions, or 4.
Do you take into account illusions if someone doesn't ask a question level 1?
Oh, I see. You want to ask another one? Is that what you're saying?
No.
And there's more food if you're hungry. I thought there were supposed to be some sandwiches also. Did they arrive? No? Yeah, they were supposed to be, but... Okay. Yeah.
I don't remember what slide it is, but there's a slide that said and every CPU has like a cache flush global, cache flush global.
Yeah, that's related to coherence.
Yeah.
That's again to make you think. There may be multiple answers in that one. Let's see. I think it was in the lecture that talked about coherence. Actually, the previous lecture that was open. This one, right? Yes. Do you have a question on how these work, or?
What are the answers to these?
Oh, okay. I think we briefly walked over this in the lecture. So, can the programmer? The question is, can the programmer ensure coherence if caches are invisible to software? And the answer is no, right? Programmer cannot change something that's invisible to software. Here, what if the ISA provided cache flush instruction? Let's take a look at 3 different kinds. Let's take a look at one thing that doesn't work, or that doesn't easily work. Flush local A. Here, the instruction specified as flushes invalidates the cache block containing address A from a processor's local cache. So, and remember, these are fiction. This is fiction. I'm just making up these instructions to motivate coherence. So what does flush local A do? Processor, cache block A. This says invalidate cache block A. Processor 1. Let's say processor 1 also cached cache block A. And I guess when would you use flush local? So what is the coherence problem? Let's go back to A. Coherence problem is you have 2 blocks cached, and one processor writes to it, and the other processor has no clue that the other one wrote to it. So the other processor later accesses the block in its cache that's stale, that was not updated, or that was not invalidated, and gets the wrong value. Right? So we want to prevent that. And assuming that we don't have hardware coherence, can we prevent it with the flush local A instruction? I would argue that we cannot. Right? So what do you need to do to be able to do this? Processor 0, let's say processor 1 is writing to cache block A. Somehow, when this happens, other processors need to invalidate the blocks. Right. So some other processors need to flush local. Well, one thing you could do is whenever you're done with the block, you could do flush local. But then you never know when some other processor writes to the block. So this doesn't work, right? You need something like this, perhaps. Yes?
So if you have like a thread and you can't look at other processors' caches.
Yeah.
Is it possible for you to like have something like this where you can flush other caches?
Okay, that's the global A. Yeah. This is where we're coming toward a solution here. So if you do flush global A, basically here, the idea is to, when you're writing, what does the instruction say? Flushes or invalidates the cache block containing address A from all other processors' caches. So when a processor needs to write to A, it basically first does flush global A. The effect of flush global is invalidating A from other processors' caches. Now this is nice. Now this processor can write to it. Is this enough? It turns out this is not enough, right? Why? Yes.
Don't you at least need some atomicity between flushing and reading?
Don't you need some what?
Like, there's a race condition if you just...
Absolutely, yeah. That's why it doesn't work, right? Yeah. What could happen is this processor does flush global A, and before it does the store, some other processor fetches A into its cache. Well, you've already done flush global A, and now you're going to write to it. And this A has some other value, 2000, and this processor already fetched 1000 right after processor 1 did the flush global A, but before processor 1 stored. Could happen. Right? That's the problem with this kind of instruction. So what you really need to have is an atomic instruction that does flush global A plus store to A at the same time. Right?
So we're assuming over here that the load instruction does not look at the other cache.
Yeah, that's right.
It looks at the memory.
Exactly.
If it was implementing that part, then
Yeah.
it shouldn't be a problem.
That's right. So that's why we need to go into hardware coherence, right? It's hard to provide these primitives that exactly do. There are other problems with this also. You can poke other problems into it. I gave you one problem.
And
Yes.
You can also have problems with stores, right? Because if I do my flush, then the next guy does flush, store, and then I do my store.
Yeah.
So it's in both, too.
That's right, exactly. So my solution doesn't necessarily work also. You need more than just atomic flush global store. So the other thing, you could do a flush cache, flush invalidate all blocks in cache X. I guess this is kind of similar to flush global A, so it has similar problems, if you will. So I don't think any of these solutions work well, if you will. You could make things work well. You could lock a page, for example, at the page level. And some systems actually implement coherence by locking pages. Such that what you do is, what the operating system can, or what a thread can do is, it says, I would like to lock this cache, lock this page, and no other thread is given access to that page. If you have that kind of support, that way you can ensure coherence. But that's very costly in software. So this was all motivation for hardware coherence. Is this clear? Okay. Now we have 5 people. Counting up. I guess we can never. Oh, we can go down. That's right. Yeah, we can reset the count. We've covered a lot of material, right? Hopefully. So you know everything. There are no questions. Now questions will come up. Yes?
So you can do run-ahead execution in 3 ways. Right? You can run it on a separate core. You can run it on the same core with different thread contexts. And same core with same thread contexts.
So run-ahead execution, the way we discussed it in class, is a specific mechanism. Which is when you get to a cache miss, and that cache miss becomes the oldest instruction, the load miss, checkpoint the architectural state, and go into the speculative processing mode where you continue executing instructions, except speculatively. And the whole goal is to generate prefetch requests. And when the cache miss returns back, you go back to the checkpoint and re-execute everything. That's a very specific mechanism, which means that those 2 other things that you said, the run-ahead execution happening on a separate core or a separate thread context doesn't apply here.
Therefore, just pre-execution based prefetching.
Yeah, that's right. What you said applies to thread-based prefetching, for example. When you fork a thread to do prefetching, that thread could be executed on a separate core, on the same core in a separate thread context, or you could decide to schedule that thread somehow only when this thread stalls, if you have that hardware support. Similar to running.
Again, what are the, like, I guess not for running for like thread-based prefetching. What are the advantages or disadvantages of the
Okay. Okay, yeah, let's go through that. I don't need to pull up the slides unless someone wants me to. Let's see. I guess we've almost exhausted the space here. So just to give context to everyone, we're talking about thread-based prefetching. Remember this picture? Maybe I should pull up the slides, but that's okay. We have this load instruction we want to prefetch for, and what we do is we have a thread. We fork a thread that basically is a subset of all of the instructions that is feeding that load that gets executed. So this is a pre-execution thread, we called it, right? And at some point it gets forked, it gets executed in parallel with the main thread, and the hope is that by the time the main thread executes this load, this thread prefetched that load, and cache miss happened, and that cache missing block was placed into the cache. And when the main thread executes this load, it's a cache hit. That's the idea of execution-based prefetching, or thread-based prefetching. Now the question is, where do you execute this thread? There are three options that we discussed in class. One is on a separate core. So what would this look like? Now you have two cores. Remember, L1 is always part of the core. Hopefully you know why. Core 0, core 1. And let's do this. A shared L2, if you will. The second option is on the same core, but on a different thread context. The idea here is you have a multi-threaded core, so you can execute multiple threads. You have core 0, and you have thread 0 and thread 1. And they share the L1 cache because it's on the same core, and they have an L2. So one context has the main program, one context has a speculative thread. And the final option that we talked about is, now you have a core that doesn't necessarily need a thread context. You have only one thread context, thread 0. Actually, here, thread 0, thread 1, let's be consistent. And what happens is when this thread 0 and the main program stalls, you start executing this thread. What is a stall? It could be a cache miss. Okay. So it's the same core, but when main thread stalls for some reason. Okay. So you're asking what are the advantages and disadvantages of each option. I guess you could come up with many, but let's go through the main things. Actually, this was a previous exam question, I think, right? So advantages of this and disadvantage. Well, okay. What is the advantage of this on a separate core? Well, the advantage is now this pre-execution speculative thread doesn't interfere with this thread, right? So if you no interference, I'm going to say no interference. I don't want to write very long. It's in the lecture slides too. If you want, I can pull up the lecture slides. Okay. No. So this thread, the speculative thread, doesn't interfere with the main thread, which means that both threads can make fast progress now. I don't know if there's another advantage. There may be, but let's look at a disadvantage. One disadvantage is now this speculative thread is not prefetching into the L1 cache, right? It has its own separate L1 cache that it prefetches into. It's prefetching into the L2 cache as well as L1 cache. So in a sense, it's not as good as this part, right? This thread is prefetching into L1. Even if this thread prefetches accurately, the main thread needs to get an L1 miss to access that. So basically only prefetch into L2. Okay? Which means that longer latency for the main thread. Well, what other disadvantage is there? Well, you need now 2 cores, right? In a sense, it's a more costly solution in terms of energy efficiency. You're really running 2 cores. Okay, let's take a look at the second one. Here, the advantage, the disadvantage of this is an advantage of this one, right? You're prefetching into the lowest level cache possible, such that the main thread can get an L1 cache hit, right? Okay, I'm not going to write this down, but basically L1 cache hit. Also. What is the disadvantage? Now the disadvantage is this. There is interference. These threads share some pipeline resource, right? Let's say it's a fine-grained multi-thread machine. Every cycle you're fetching from a different thread, which means that you've held the throughput of each of the threads, at least the pipeline throughput. Okay? So there's interference, heavy resource interference between the threads, which means that each thread is running slowly. Is there another thing? Yes, there's another one, which is now you need a multi-threaded processor, right? Okay? But in essence, it's a similar disadvantage to 2 cores, except it's hopefully cheaper. Here, we're running the speculative thread on the same core as the main thread, but when the main thread stalls. So what is the advantage? Cheap. Right? You don't need a multi-thread processor. You don't need separate thread context at all. You just multiplex the same thread context. I guess the disadvantage, well, now the disadvantage is you're not prefetching very well probably, right? Meaning this thread, you really would like this thread to run while this thread is doing some other work. You really would like this main thread to stall while this thread is actually trying to run. But what if it doesn't stall? So you may not be able to do good prefetching in this case, because you're really not running the 2 threads in parallel. So, not running 2 threads in parallel which means that you may not be able to do good prefetching. Okay? Are there other disadvantages? Well, you are interfering with the execution of the thread, main thread, a little bit. So it has a little disadvantage compared to this one. Because when this thread stalls, in order to be able to switch in the speculative thread, prefetching thread, you need to flush the pipeline. So that has an effect on the performance. It's not like this one. Okay? Now there are other disadvantages also. Here, if you're prefetching wrongly, here you're polluting the L1 cache, right? Here also you're polluting the L1 cache. Whereas here, you're not polluting the L1 cache, because you're prefetching into a separate L1 cache. You're polluting the L2, but not the L1.
Is there a way to fix the first disadvantage on the separate code though? Like you could.
You mean this one?
Yeah.
Only prefetch into L2.
You could possibly also generate a cache fill notification for the other L1.
You could, that's right. So if you actually designed your hardware that way, such that it's aware of the speculative thread, and whenever the speculative thread generates a request, you not only fill your own L1, but you also fill the main thread's L1. You could fix that. You're right. Okay. Yes.
So most of the processor stall time is on L2 miss, and L1 cache pollution is, you don't want to keep on polluting L1 cache. So is prefetching usually done for L2, or is that again a decision?
That's again a design decision, right? Many processors actually have both do prefetching into L2 as well as L1. And they do prefetching between the cache levels also. But the bigger gain, again, Amdahl's law comes from reducing the big bottleneck, which is, if your memory is the big bottleneck, which is usually the case, prefetching into L2 buys you most of the performance benefit. But then there may be programs that actually fit into L2, but do not fit into L1. Right? In that case, prefetching from L2 to L1 helps because the bottleneck in those programs are actually the time you spend waiting for the L2 to respond, not the memory to respond. What else? We could have another lecture on prefetching right now. It's a fascinating topic, I think. And this is, again, a general mechanism. It's not only, again, this is the way processors do prefetching. Your systems do prefetching also. Are you guys aware of that? Some of you are. Like, there are prefetchers in your operating system that actually keep track of what applications you run at what time. Or under what conditions. People actually develop these prefetchers and sometimes start up the applications early. Prefetch them into the main memory from the disk. I won't tell you exactly what operating systems, but there are prefetchers that are in your operating system that do this. Yes?
Can you use prefetching information for cache covering? So instead of invalidating a block, it's created something like that.
How would you do that?
So one core detects that it detects that this cache block is going to be used later, and at that time or in the same time frame, another L1 cache says that okay, I'm going to write into this. So all the other caches have to invalidate the block.
Okay.
But you already have information in another cache which says that we might potentially need this block.
Because of the prefetcher.
Exactly.
I see.
So instead of just invalidating it, you update it and maybe mark it.
That's a good idea. You could. I don't know of any processors that do that, but that could be interesting to examine. If your prefetcher is doing accurate, especially, right? That's good information. That way, that could be one way of deciding between an update or an invalidate. What else? Yes.
How are you thinking of dividing up the exam topics? Like, how are they weighted?
So that's a good question. Everything is fair game at this point, I think. I mean, you should know the basic concepts for sure. We've covered a lot of things. I don't think I will necessarily bias it toward the end. There will be questions toward the end, so there will be some bias, but it won't be like 80% of the questions are going to come from the how many lectures we covered after the last exam. So I cannot tell you an exact number, but it won't be heavily biased toward the end. It will test your understanding across the entire course. Okay? But there will be some bias toward the end. So I expect questions on prefetching, for example. I'll give you that. Yes?
Are you expecting it to take us the entire 3 hours?
It's good, yes. But this time it will be you won't have as much of a time crunch. I promise that. It won't be as long. Just because it's 3 hours, we're not going to increase the length of the test by, what is that? 33%. Because it was 1 hour, 15 minutes before. Well, a little bit more than 33%. But know the previous test really well. If you know the previous test really well, and understand the concepts. That's not enough, of course, because there will be different questions. I don't intend to ask the same questions again. Yes?
Could we go over thread warps and how they help with CMU processing?
Thread warps. You mean GPUs?
Yes.
Okay, so that's a concept we didn't cover in detail. So I will not expect you to know how that works. Thread warps work in a GPU. That's really a 742 concept. I can still go over it if you want. Where is this? SIMD. Right. Should be here. You should know how SIMD works, vector processing works. Oh no. Did I send information or not send information? Don't send, okay. You wanted me to send? It's opening everything. That's not good. What did we want? We wanted this one, right? Yeah, not this one. We're almost there. Yeah, thread warps. Okay. So what is a thread warp? A thread warp is essentially you write a bunch of scalar threads. Actually, let me go back. Okay, it's not here. Okay. It's here actually, yeah. So if you look at this is a loop iteration, right? This loop iteration, every iteration can be in parallel. Right? Which means that you can write a single thread for each iteration. That's the idea. So this is the sequential code, iteration 1, iteration 2. Another way of looking at it would be, remove that vectorized for now. Think about this as thread 1, thread 2, thread 3, ... And so you could have n threads doing the same thing on different elements of data. Right? So think of this as a scalar thread with 1, 2, 3, 4 instructions. Another thread, the same thing, same thread. And replicate it side by side. And execute the same instruction from the same thread at the same time. Now what you can do is, you can group these threads such that they execute the same instruction at the same time. Right? Because they have the same program counter for this load, except they operate on different data. So that's the idea of a thread warp, basically. Multiple threads that have the same common program counter that can execute the same instruction at the same time. And that's how a modern GPU works. The programmer writes a program like this, multiple threads that do the same thing, and the GPU somehow groups them together, and I didn't tell you how it groups them, and ensures that threads execute the same program counter at the same time. That's the concept of a thread warp. A set of threads that execute the same instruction on different data elements at the same time. If you look at this, it's very similar to single instruction, multiple data, right? You really have a common program counter, and you're executing that instruction at that program counter on all threads on different data elements. So that's how it relates to SIMD. Except the programming model is not SIMD, right? You really write a thread here. Whereas, remember the vector processor code that we wrote? It's really a SIMD programming model. We don't look at threads there, right? We had a vector instruction. That's the major difference between a SIMD, a vector processor, and a GPU. How we program it. Does that make sense? And beyond this, you really don't need to know anything else. I'm not sure if you really need to know what I said also for the purpose of the exam, but it's good for your education, I think. There's a lot more detail that I go into in 742, like how this architecture actually schedules these warps. That's interesting, right? But let's not go into that right now. That'll be a different lecture, a different course. What else? Yes?
Can we just go over kind of like the directory coherence model?
Oh, okay.
So I found like the diagrams confusing.
Okay, sure. Yeah, that's why coming to the lecture helped. But you were at the lecture. That's okay. That's what the review session is for. Okay, actually, let's go through the diagrams also, just so that we do the same example again. It's simple. The idea is very simple. Usually, simple ideas get implemented. That's why it's good to build up simple ideas. Let me see. Not more coherence. I thought this was already open, but no, it opened the third version of it. Okay. So what is the idea? The idea is you have a directory, logically central directory, that keeps track of where the copies of each cache block are. Right. So think of this as, okay, you have a processor 0, 1, oh, that didn't look like a rectangle, and caches that can cache blocks. And you have main memory. The idea is memory is divided into cache blocks, right, logically. And with each cache block, you store some information telling where the cache block is cached in the system, in the entire system. And what is that information? Well, in our example, I gave a bit vector, right? Suppose we have 4 processors like this. We have 4 bits, 1 for each processor. And these bits tell whether the block is in processor, whether or not the block is in that processor's cache. Right? So initially, in this example, we don't have the block in any of the processor's caches. Right? Let's say this is this block, block 0. Block 1, 2, ... And you have this information that's kept for each of the blocks in memory. 1 bit per processor. There's also another bit, which we will use, called the exclusive bit. So what is the purpose of the exclusive bit? Do you guys remember? This says the block is in one processor's cache, and that's the most up-to-date copy. Right. So if you look at this, if you look at the lecture notes, it indicates that the cache has the only copy of the block and can update it without notifying others. I said it in a different way here. But initially, it's not exclusive. If the block is in memory, it's not in any cache. Right? Exclusive means that some cache has the most up-to-date copy, and the copy here cannot be trusted. Okay? Is this clear to begin with? You want me to go over this? No? Oh, okay, no? Anyone want? Yeah.
Wouldn't it more so be a modified bit then? If you're saying that the block that's originally in memory can't be trusted, then wouldn't that be more so than an exclusive bit? Wouldn't that more so be a modified bit?
Well, you could call it whatever you want, right? It's called exclusive, but you could call it a modified bit. The key is when is this bit updated? Right? Let's call it exclusive bit for our purposes. It means that the processor that has the block exclusively. You could call it modified bit, saying that the processor that has the block modified, and no other block has it. It's really what you call the thing, if you will. Yes?
So a directory has one entry for every block in the cache?
Yeah.
There's no eviction or replacement?
No. The directory has a bit vector like this for every cache block that is in memory. Right? So you could have many cache blocks. So think of your memory divided into cache blocks, logically. So if you have a 4 gigabyte memory, your cache block is 64 bytes, you have a huge directory. Right? That's part of the problem with this scheme. Right? It's not that you have this for only those cache blocks. Right? Because the purpose of the directory is whenever a processor wants to access a cache block, it goes to the directory saying, directory, I want to access this cache block. Right? Well, let's go through this actually while we're at it, so that everyone is clear on this. So initially, no cache has a cache block. So we're going to take a look at block A. Processor 1 says, I want block A. Processor 1. I want block A. So it sends a message to the directory saying, I want block A. Let's call this block A now. The directory says, oh, nobody has a copy. Then my copy must be the right copy. And it's going to send the block to processor 1. Now processor 1 has block A. And set the bits corresponding to processor 1 in the directory saying that now processor 1 has a copy. Now processor 1 did not ask the block to write to. It could have said, directory, I want the block to be exclusive. In that case, the directory would have given the block and set the exclusive bit. Right? But the processor 1 didn't do that. Processor 1 said, I'm going to read the block. I'm not going to write to it. Okay? So the directory knows that processor 1 has a copy and it's not going to modify it. Now processor 3 takes a read miss on block A. Processor 3 says, I want to read block A. Directory, give me block A. Now the directory knows that only one processor has it and it doesn't have an exclusive state, which means that this copy is the most up-to-date copy still in the system. So it sends the block to cache 3, processor 3, and sets the bit for that processor. Right. Next, what happens? Processor 2 takes a write miss. So this is more exciting, if you will. So processor 2 says, directory, I want to write to block A. And if you remember, write is the same as read exclusive. You can use the same word. I want to take block A, and I want to have the only copy in the system because I'm going to write to it. So what does the directory do in this case? Directory sees that block A is present in processor 1 and processor 3's caches. So what it does is it sends invalidate requests to processor 1, invalidate A, and the same request to processor 3, invalidate A, and waits for a response. After some point, processor 1 invalidates block A and sends a response to the directory saying, acknowledging, I acknowledge the invalidation of A. And processor 3 does the same thing. Let's do this. Processor 1 sends, I acknowledge the invalidation of A. At that point, directory sets this bit to 0. Processor 1's bit to 0 because processor 1 doesn't have cache block A anymore. Same thing happens with processor 3. Processor says, I acknowledge the invalidation of A. I don't have it in my cache. Now the processor directory sets processor 3's bit to 0. Now the directory knows no one has it in the cache, in its cache, has block A in its cache. And processor 2 requested it. Now processor 2 can get the copy to write to it. So it sends block A to processor 2, sets processor 2's bit, saying that processor 2 has a copy, and it has an exclusive copy because it's going to write to it. Now processor 2 has the exclusive copy to A. No other cache has it. And processor 2 knows that it requested it to be exclusive. So it knows that it can modify it without notifying the directory, right? Because the directory knows this is the only copy in the system. The directory is not going to give the stale block to anyone. Okay. So that's what I mean here. So per cache block, you need to have a private bit saying that you can actually write to it because you got permission from the directory to write to it. Okay. Now let's see what happens when P3 takes a write miss. Okay. P3 says directory I want to write to block A. Now what happens in this case? In this case, the directory knows that P2 has the block and P2 has the modified copy. One thing it could do is, well, let's see, what did we say? We said it sends a message to processor 2 requesting the up-to-date copy because this copy is not trusted, right? Because processor 2 has the exclusive. So it says, processor 2, give me back your copy of A, invalidate it, and that's it. That's the message that's sent. But you want processor 2 to invalidate it because some other processor 3, requested to write to it. Later, processor 2 responds back, acknowledging, and sending back cache block A, the modified version. The directory updates block A in memory, sets processor 2's bit to 0, and exclusive bit to 0. Now block A is up to date in memory and in no processor's cache because processor 2 invalidated it. Now the directory can send block A to processor 3, which requested it exclusively, and it does send it back. Send it to processor 3, sets processor 3's bit, and sends it to the exclusive. Right. Yes.
Do you have a dirty bit in this and not write to memory every single time you store something?
Say it again.
Could we, you know how we have a dirty bit in and use write back in distant cache?
Okay.
Could we do that over here as well?
Well, you do have a dirty bit in your cache, right?
Okay.
So when the block is exclusive in your cache, you can write to it,
right,
and it could be dirty.
Okay. But when another processor wants it, can we not use that block and just transfer it to the other cache?
Oh, you could do that. Yeah, you could optimize the scheme.
Okay.
So what the directory could have done is not request this block, but if you have a more complicated mechanism, the directory could have said, processor 2, give your block to processor 3, invalidate your block, and ensure that happens, and after that send me an acknowledgement. Right. So that's a more complicated protocol. Okay? There are many ways of optimizing these protocols. This is one simple example, if you will. Okay, is this clear? I guess we don't need to go through the last read miss. That changes the state a little bit also. What else?
So if you do have that read miss, you're going to update your block A and memory there.
Okay, let's do the read miss. That's read miss, right?
Yeah.
Okay, processor 2 takes a read miss. Processor 2, now it says, I want to read block A. What happens? The block is not, the block A in memory is not up to date because processor 3 has it exclusive. What the directory does is, well, yeah, the same way here as we talked. One simple mechanism is directory says processor 3, somebody else is needing this block, give me your block. Okay. I guess let's see. It really depends on the protocol. I guess here we did not invalidate. And there's no reason to invalidate it in processor 3's cache, right? So directory says, processor 3, give me your block. That's it. Right? So processor 3 writes the block back and can keep it in its cache. And it was here, remember? What this does is it's not exclusive anymore, right? Processor 3 doesn't have it exclusive anymore. And now the directory knows that it's got the block and it has the up-to-date copy. It supplies the block to processor 2 and sets the bit for the processor 2. Now you have a shared copy across processor 3, processor 2, processor 3, and memory is up to date. Okay? You could have done it in a different way.
So, did these lines represent Ethernet cables over a network, or how are these connected?
No. This is this is made over main memory, right? This could be any interconnect, right? This could be a bus. That's the beauty of a directory, right? You just need to implement this protocol over some type of interconnect. It could be, you're right, it could be Ethernet also. But in your system, the way I'm thinking right now is it's really some interconnect that connects main memory to the caches. So my description of these lines are really high-level messages. These are not hardware lines. These are high-level messages that are sent on some hardware. Go ahead.
So, in the last lecture, we spoke about accelerated critical section, right?
Mm-hmm.
So, I don't understand how they avoid ping-ponging of locks. Because, when you test a lock, when each particular parallel thread that's running on the small cores tests a lock, doesn't the test also require acquiring it?
No. So they don't. What happens is, actually, maybe I guess I forgot that these exist. It's very tempting to jump and pull it down. Okay. So you replace the critical section with a special instruction saying critical section call. So you don't test the lock.
But to get into the critical section, you need to test it.
No, the critical section happens in the big core, large core.
So is the testing of the lock included in the critical section?
That's right, yes.
Okay,
that's right. So the small core does nothing about the critical section. It says, I got to a critical section, let me send everything to the large core and let large core handle it. Okay. So all you get is a critical section call. I want to execute this code that's at that target PC. Okay. It includes the lock, exactly. See, acquire happens here. Acquire of the lock. Yeah. Otherwise, you would have the lock ping-ponging here, right?
Do you have a push A and a pop A? Does that mean you're preserving a register context when you switch from?
That's right. That's right.
So what is the asymmetrical core, multi-core user from the ACS?
So ACS is one way of taking advantage of an asymmetric multicore. Asymmetric multicore, if you will, is a substrate, right? Instead of having homogeneous cores, you have this. Well, if I can draw it, it'll be better, but what did I screw up here, you think? Oh, this. Okay. There you go. So you have one large core, or n large cores, and a bunch of small cores. The question is, what do you execute here? So one thing you could execute is serial sections. serial bottleneck, if you will. And in a sense, that's the first thing that comes to your mind, right? So you have this abstraction of serial portion, parallel portion that I kept drawing in class. And when you get to the serial portion, why don't you execute in the large core? What ACS does is, basically, in addition to these serial sections, when a thread in the parallel portion gets to a critical section, also send it here. Okay. So locks happen in this parallel part, right? Lock, unlock. Otherwise, you don't need the locks in the serial section because you have only one thread. Lock, unlock. So it's one way of taking advantage of this asymmetric multicore by sending these critical sections and executing them here. Make sense?
So what would the large core be doing when you don't have ACS?
Oh, when you don't...
Like, would it just be like idle?
Yes.
It would.
So that could be one thing. There are design choices, of course. You could potentially be executing other threads, but that would complicate things a little bit. But you can assume that, I mean, if we ask you a question, actually there were some questions in previous exams, we will tell you whether the large core is actually doing nothing or if it's doing something. But the way it's proposed in this paper is large core is doing nothing other than executing the serial part or critical section. If none of them exist, large core is idle, which may not be the best design choice.
And so previous exams, so do you have practice finals available?
So that's homework 7. At least homework 7 test part of the concept. There is no practice final, right? Is there a practice final?
We don't have finals.
Yeah, we don't have finals. Yeah. But you can. Is it homework 7? Homework 7 is intended to serve you as a practice final for the last portion of the course, if you will. That's why we provided homework 7. But just for the last portion. For the other portions, you already have midterm 1, midterm 2, and other questions. I would actually encourage you to go and solve those questions. Maybe time yourself also. That would be a good exercise, probably.
Which ones?
Even previous midterms as well as homework 7. That could be a good way of studying.
So for the asymmetric processor, when you don't have the ACS, your large core is essentially just idle. That's like the main difference in what we discussed.
Oh, when you're just executing serial. Well, so it doesn't make sense to not execute anything here, right? Let's say you don't have ACS. Yes. Let's say you don't have ACS. When you have a sequential code section, your large core is not necessarily idle, right? And so, okay, you're in the sequential part of the program, the sequential thread executes. You're not in the sequential part of the program, then you could execute the parallel threads here, but what you could do is you could execute 4 other threads here, right? What you could do is you could time multiplex. Okay, backbone. Yeah. Does that make sense?
Yeah, I was just like, I was having trouble figuring out like what the large core did.
Oh, what the large core did when in the parallel section.
Yeah.
Yeah. Yeah, you could execute threads here, right? There's no reason not to execute them, otherwise you're wasting.
When you have 2 things, because I thought you said like the performance was like proportional to the square root. So if it has 4 times the area, then isn't it like twice as fast? So
No, you could time multiplex, right? The 4 threads here.
But
I mean, you need to make it happen, of course. There could be overheads. You're right.
But if you time multiplex the 4 ones, then won't they each run half as fast as the other small ones?
No, I.
Because if that's taking up 4
I see.
units, I thought you said that would get performance about as fast as the square root of 4. So
Or you could multi-thread this, right? That's actually a more reasonable design choice. Having multi-threading here. So remember, that was for a single thread. So the performance of this large core is for a single thread.
So
It's a square root for a single thread.
So you can like parallelize some of that.
Exactly. Exactly. You can design this hardware to get good performance on 4 threads.
So, was it that the large core the larger core typically in these designs can execute things with the performance, or at like the square root time of the other ones?
So that was the rule of thumb we used. That's
okay,
right. For a single thread. So if you want to execute a single thread here, the performance of this is twice the performance of a small core, because this has 4 times the area. Well, you could have another function, right? This is just a rule of thumb, if you will. Because somebody actually plotted these numbers, and that's over a large number of processors, and that's what they saw. It's really empirical. Like Moore's law, right? It's also an empirical law. What else? No questions? Have you guys started studying yet? No. You should really start studying. Yes?
Can we discuss the matching thing in directory-based programming?
What thing in directory-based class?
Knacking.
Knacking. Okay, let's take a look at knacking. So it must be hiding here. There it is. Oh, maybe it's not hiding here. Okay. Because it's the next lecture. So I gave you one example of knacking, right? That's right. Here, yes. Okay. So we have this directory, and we have 2 processors. Both want an exclusive read request for the same block. It's a write request. Which one does the directory honor, if you will? Well, let's say the directory picks this processor, and it gives it the data, and it gives the exclusive writes. So what does it do? The question is, what does it do to processor 1? Processor 1 requested it, right? One option is to have the directory buffer that request. It could have a buffer saying, this processor requested it, and after a while, I will grant that block to this processor. Now that has some trade-offs. I'll let you think about it. One other option is to say, processor 1, you cannot get it right now, try again. And that's the idea of knacking. The directory says, processor 1, too bad somebody else requested it at the same time, or at a similar time, or somebody else has it at this time. So I'm not going to grant you this request. So try again. That's the idea of a knack. Negative acknowledgement. Is this what you were asking? Or do you want to continue the example?
I was going to ask, after this, E1, I think P0 gives data directly to P1.
Yeah, so this is an optimized protocol protection. So let's see what happens. Well, processor 1 is unhappy, of course. Later, after some time, processor 1 tries again, right? Because the directory told it to try again. At this point, the directory tells processor 0, processor 1 is requesting it. So invalidate your block and supply the data to me as well as processor 1. Or actually, this it doesn't make sense to supply the data to directory, if you will. This is called a revision request. You don't need to know the details as long as you can reason about how this could work. Here, the processor 0 sends a message back to the directory saying, directory, I acknowledge your invalidation. Remember, all the invalidations need to be acknowledged, right? Otherwise, it doesn't work. Otherwise, the directory has no clue which cache actually has the data or doesn't have the data. So this is a revision request saying that it's actually an acknowledgement. I acknowledge your invalidation, and I've also sent the data to processor 1. Does that make sense? This is one optimized way of handling things. Now here, what I described was, you could do it this way. Processor 1 asks for the data. The directory says processor 0, somebody else is asking for the data exclusively. Invalidate your block and give it to me, because you have the most up-to-date copy. And let's ignore this part. Processor 0 could have replied, directory, I've invalidated my block, here is your copy, up to date. Now take it and do whatever you want with it. And now directory has the up-to-date copy, and it knows that processor 1 is requesting it exclusively, and processor 0 has given it up. Now the directory can send the block back to processor 1, right? This is just a shortcut, if you will. And this shortcut works nicely because it basically reduces some latency. And if processor 0 is really close to processor 1, and if you have a scalable interconnect, like a mesh, for example, this transfer is much faster, right? Yes?
So what happens if, like, processor 2 has a value, has a cache block in the shared state as it does there, and then it has to evict it because it wants to read in some other block? Does it, like, tell the directory?
Yes. Yes, it has to communicate with the directory.
So then does the directory always know exactly when things are in each cache?
Exactly. Yeah, that's the idea of a directory. Whenever you write back a shared block, you need to tell the directory. Or whenever you evict a shared block. You can optimize these things, but that's the way we describe the directory. The directory has perfect knowledge about what block is in whose cache. I mean, one way of optimizing that is the cache can silently evict the block, right? And the directory sends an invalidation request to the cache, and the cache infers that, oh, the directory is stale. Right? So that could work. That protocol can be made to work without notifying the directory on a clean write-back, or a clean eviction, if you will.
Also, when you do the read exclusive here, and then you do the write, is that atomic? So there's no chance that, like, the other cache could make its request again and cause the eviction?
No, it's not atomic, but it'll all work.
Wait, so then couldn't you just keep going back and forth
Yeah,
forever?
you could. You need to design your protocol nicely, right? You could. There's nothing that prevents this, right? So you could design your directory such that directory knows that, oh, I've given this block read exclusive to some other cache in the last 5 cycles, so I'm going to nag this request. You could have a timeout, if you will, right? So that's the difficulty in designing these protocols. You get into a lot of race conditions, especially if your interconnect is not a bus. So the protocol you designed for Lab 7 was one of the simplest possible protocols. Real systems usually have directories, especially if you want to scale the system. But almost all real systems have directories, directory-based coherence. Yes?
So you talked about, like, if it's like you have too many, like a lot of cores, then you, like, distribute the directory.
Yes.
Like, I don't understand exactly how you, like, what do you distribute?
So the directory doesn't need to be central, right? Here, if you have a central directory for all blocks, what happens is every request comes to this directory. And if you have 10,000 processors, this directory can be overwhelmed. The idea of a distributed directory is now you partition the nodes. You say, this is my memory. Blocks that are at, let's say you have 2 partitions. Blocks that are at address 0 through n over 2 are in this node, in this directory, in this partition of the directory, and the other blocks are in this partition. Now you can have 2 nodes serving as a directory. And you exactly know when a processor accesses a block, it basically checks, is it in this half of memory or is it in this half? And sends the message to the right directory. And you could increase this, right? You could increase the partitions.
I was more thinking that you partition to reduce, like, propagation delay.
Mm-hmm.
So you keep it nearer to the processor.
So that's difficult. That's more difficult, right? Then the question is, so when a node accesses an address, they need to know where the directory is. Well, actually, that's very strong, but the way we describe it, they need to know where the directory is. So if your address tells where the directory is, then that's nice. Whereas there are other, what you're suggesting is somehow changing the node based on where it's cached, changing the directory based on where the block is cached. That's a lot more difficult. Now we need to figure out where the block, which directory took us out. Right? That's very tough. Yes.
Yeah, it seems like this could still potentially not reduce the load on a given directory, though. Because, like, what if I only access stuff in the lower half of the node?
That's right. Yes, absolutely. The hope is that it will reduce, but
maybe you should have like a more complicated hash function.
Sure. So you've learned all of these in the class, right? You reducing directory complex. You basically hash the address in a different way. Absolutely. Instead of taking this bit, if you will, maybe take some bits from the lower end, or maybe hash these bits to get to figure out the directory. Looks like we're losing people.
Thanks.
Sure. Good luck on the exam. Study hard.
Or you could just make it easier and then we'll all be fine.
Well, it's hard for everyone, right? I don't think it's that hard. Is it? Were the exams hard?
Yes.
Lots of
exams.
We learned about this in cognitive psychology. It's the knowledge effect.
This will be easy.
You're an expert, so you find it
What I
easy.
learned in computer architecture was.
Well, you know these concepts now, right? So if I ask you about how to reduce the size of the directory, you can tell me. Maybe. Or if I ask you about how to partition the directory, you can tell me. Or you can calculate the size of the directory, right?
That's annoying because that requires arithmetic.
So if I give you the memory size, cache block size, and the number of processors in the system, you can calculate the size of this directory, right? Simple. Yes?
Does the directory actually hold the block data, or is it just holding like the status?
Yes, it is holding the status. This is really the memory, right?
Okay.
Yeah. Yes?
If you have a large core and several small cores, so do you still use a directory there? Can you use a directory?
Yeah, I mean, they're orthogonal concepts, right? There's no reason.
Then the directory needs to store information about all the cache blocks which are in the cache, and you have one larger cache and like several.
No. So again, the directory stores information about every possible cache block in the system.
Oh, okay.
Not only those cache blocks. Memory is logically divided into cache blocks. The directory has information about every single one of them. So even if a block is not cached, the directory has a bit vector for that block, right? And that bit vector is all zeros. Right. So a good exam question, for example, would be, and I'm not going to ask this anymore, but if the bit vector for a cache block in the directory is 0, all zeros, what does this tell you? And your answer would be, exactly, that block is not present in any cache, right? Okay. Yes?
It's just like a minor question about reading these diagrams.
Okay.
Because I noticed this on a lot of them. What exactly does like the read exclusively? Because it says it's like a write.
Yeah, it's right. Exactly.
Okay,
it's
so
exactly right. So, that's why attending the lecture is important. Oh, you're in the lectures, though. That's it. I keep saying that, right? So it's also somewhere here. But in the lecture, I said that read exclusive is a write request, right? Actually, here. So bus write plus or bus read exclusive. It's the same thing, basically. Whenever I say read exclusive, it's also a write.
Just like no, it's exclusive.
Yeah. Yes.
So I don't know. This felt like a theoretical question, but like Can you, like, so we spoke about Snoopy caches and directory-based caches, right?
Yes.
And we spoke about Messi. So, like, is Messi something that can be incorporated with any of these?
Yes. Yeah, we discussed this in the lecture, right? Messi is a protocol, if you will, that can be incorporated with a directory or with a Snoopy cache.
So what are those called? Protocols as well?
So, that's a good question. In a sense, Messi, the way to think about it is like a state diagram, state transition diagram for the blocks. Right? You could implement that state transition diagram implicitly with a Snoopy cache. Then you really need MESI states in each cache block, or explicitly with a directory. Right?
So the interface.
Yeah. Exactly, yeah. So you could implement any of these coherent state diagrams, if you will, with Snoopy caches or directories. The main difference is Snoopy cache does it implicitly because you have a substrate, you have a broadcast substrate where every cache is aware of what happens in any other cache. Whereas directly you have these explicit requests. That's the major difference. And explicit request means indirection, right? And that enables scalability. Okay. You can actually close it if you're bothered by the sun. It's good to have some sun. I got out of my office last night late and I got soaked in the rain.
This is why you always carry an umbrella when you live in Pittsburgh.
I guess that's true.
That's why I always carry an umbrella.
I didn't learn my lesson beforehand. What else? Looks like we're losing more people now. I guess everybody's ready. I hope so. Feel free to get some food before you leave. There's a lot of food left. Or drinks. Are you done? Okay. Okay, good luck on the exam.